the thing that's most interesting about this is it's a production system. It's a level of production technology that is far in advance of any automotive plant on Earth.
By the end of 2025, Tesla's Fremont factory was still using more than 1,000 robots for welding, painting, and assembly. But as 2026 began, Tesla started removing a huge number of those robotic arms from its production lines. Elon Musk then made a bold claim. Tesla had developed a vehicle manufacturing system unlike anything else in the world. The technology behind this transformation is Tesla's fourth-generation Gigapress, a massive machine designed to manufacture the company's next generation of vehicles, including the upcoming Cybercab and robotaxi. What makes this especially interesting is that Tesla is developing this technology for smaller and more affordable vehicles. So why would the company need an even larger Gigapress to build smaller cars? To understand that, we need to look at how Tesla's gigacasting revolution began. When Tesla was developing the Model Y, the company wanted to simplify vehicle production. Traditionally, a car's structure is made from dozens of separate metal components that are welded together. Tesla wanted to replace many of those pieces with a single massive aluminum casting. The problem was that machines capable of producing such enormous castings were extremely rare. Tesla searched around the world for a manufacturer that could build the machine it needed. Eventually, the company found Hydra, an Italian manufacturer that had been developing a huge high-pressure die-casting machine. The timing was almost perfect. Hydra's technology provided Tesla with exactly the kind of machine it needed, eventually becoming known as the Giga Press. The basic process is surprisingly simple, although the technology behind it is extremely sophisticated. First, aluminum alloy is heated to extremely high temperatures until it becomes molten. The liquid metal is then injected into a specially engineered steel mold shaped like the vehicle component. The Gigapress pushes the molten aluminum into every part of the mold under enormous pressure. The goal is to fill the mold quickly and evenly while avoiding air pockets, weak areas, or other defects. Once the mold is filled, the aluminum begins to cool and solidify. This stage requires incredible precision. If the metal cools too quickly, the mold may not fill properly. If the process isn't controlled correctly, trapped air can create bubbles that weaken the finished component. Tesla therefore relies on carefully controlled cooling systems to maintain consistent temperatures throughout the casting process. After the aluminum solidifies, robotic systems remove the casting, trim away excess material, and inspect the finished component before it moves toward vehicle assembly. The biggest advantage is what happens before all of this. Instead of producing dozens of smaller components and welding them together, Tesla can combine many of those parts into a single giant casting. That means fewer parts, fewer welds, fewer manufacturing steps, less labor, and a much simpler production process. It can also make the vehicle lighter while increasing structural rigidity and strength. This is why the Gigapress became such an important part of Tesla's manufacturing strategy. It wasn't simply about building cars faster. It was about fundamentally changing how cars are built, and Tesla is no longer the only automaker interested in the technology. Major manufacturers around the world are now investing heavily in large-scale die casting. Companies such as General Motors, Hyundai, Volvo, Zeekr, and XPeng have all been exploring similar manufacturing systems. XPeng, for example, has invested in a massive 16,000-ton Giga casting machine, but Tesla appears to be taking the concept one step further. The company's fourth-generation Gigapress is designed to push casting technology to an even higher level, with greater capacity and faster production speeds. That is particularly important for Tesla's future vehicles. If Tesla wants to produce millions of smaller, affordable electric vehicles, traditional manufacturing methods could become a major bottleneck. A factory filled with thousands of robots performing hundreds of individual operations can be complicated, expensive, and time-consuming. Tesla's new approach is different. The goal is to reduce the number of individual manufacturing steps and replace them with highly automated systems capable of producing large sections of a vehicle much more efficiently. That could explain why Tesla is removing so many traditional robotic arms from its production lines. The bigger strategy isn't simply about having fewer robots. It is about creating a completely different kind of factory, one where fewer machines perform far more work, production moves faster, and vehicles require fewer individual components. And if Tesla succeeds, the impact could go far beyond the Cybercab or robotaxi. It could become the foundation for a new generation of smaller, cheaper Tesla vehicles designed for mass production. That is why the fourth-generation Gigapress may be far more important than it first appears. Tesla isn't just building a bigger machine, it is attempting to reinvent the factory itself. While other automakers are still trying to catch up with Tesla, Elon Musk appears to be planning an even bigger leap in manufacturing. Tesla's next target could be a massive 50,000-ton Gigapress, far larger than the 20,000 or 30,000-ton machines being discussed across the industry. When Musk first mentioned a machine of this size, it raised an obvious question. How could something this enormous actually work? Where would Tesla install it, and could one machine really produce major structural parts for several vehicles at once? According to Musk, that extreme scale is exactly the point. The goal is to create a factory that operates at a speed humans simply cannot match. With a highly automated 50,000-ton Gigapress, processes such as injecting molten aluminum, cooling the mold, removing the finished casting, and preparing for the next cycle could happen continuously, with very little human involvement. Tesla has suggested that future casting cycles could take only a few seconds. Instead of looking like a traditional car factory, the production line could resemble a high-speed electronics manufacturing facility, moving so quickly that people wouldn't even be able to safely work close to the machinery. Surprisingly, the basic process would remain similar to Tesla's smaller 6,000-ton and 9,000-ton Giga Press machines. The major difference would be the enormous scale, speed, and precision. Everything starts with aluminum. Tesla can use both new aluminum ingots and recycled material from previous castings. The aluminum is heated to roughly 850 degrees Celsius until it becomes molten. After impurities are removed, the liquid metal moves through heated pipes into a second holding furnace. This furnace keeps the aluminum between approximately 750 degrees Celsius and 850 degrees Celsius, ensuring it remains ready for the next casting cycle. Tesla's system uses two furnaces for different purposes. The first melts the aluminum, while the second maintains the molten alloy at the correct temperature until it is needed. But temperature control isn't the only challenge. Molten aluminum must also be protected from contamination. Nitrogen gas can be used inside the holding furnace to reduce the metal's reaction with oxygen and prevent unwanted oxides. Additional processes using argon gas, rotary degassing equipment, and specialized filters help remove dissolved gases and small particles from the molten alloy. Once the aluminum is clean and ready, the mold must be prepared. Before each casting cycle, a robotic system applies a thin layer of lubricant across the mold. A small amount of soybean-based oil helps prevent the finished aluminum component from sticking to the mold. The machine then creates a vacuum inside the mold to remove trapped air. This helps reduce casting defects when the molten aluminum enters the cavity. Next, the molten aluminum flows from the holding furnace into the Gigapress's shot chamber. A high-speed piston then forces the liquid metal into the mold under enormous pressure, filling the cavity within seconds. Once the mold is filled, the aluminum begins to solidify. The newly formed casting is removed while it is still extremely hot, at around 400 degrees Celsius. It is then transferred to a cooling system, where its temperature can quickly drop to approximately 50 degrees Celsius. This rapid cooling does more than speed up production. It can also help reduce certain casting defects and improve the mechanical properties of the finished component. Meanwhile, the machine immediately prepares for another cycle. After the casting is removed, the mold is cooled to roughly 185 degrees Celsius. Robotic systems then clean the mold thoroughly, removing leftover material and preparing every surface for the next shot. This entire process highlights what Tesla is really trying to achieve. The 50,000-ton Gigapress isn't simply about building a bigger machine. It is about combining enormous casting capacity with extreme automation and speed. Instead of relying on thousands of individual manufacturing steps, Tesla wants to produce large vehicle structures continuously, quickly, and with minimal human intervention. If Tesla can make this technology reliable for mass production, the traditional automobile factory could look completely different. Rather than a factory filled with thousands of workers and robotic arms performing countless separate operations, Tesla is aiming for something closer to a highly automated production system where molten metal enters one side and large, finished vehicle structures emerge almost continuously. And that could ultimately become one of Tesla's biggest advantages, not just the vehicles it produces, but the revolutionary manufacturing system used to build them. Thanks to this highly coordinated process, Tesla can begin another casting cycle only 1 or 2 minutes after the previous one is completed. Any excess aluminum left on the finished component is trimmed off and recycled directly back into the melting process, helping reduce material waste. Before a casting is approved, it also goes through X-ray inspection. This allows Tesla to examine the inside of the component and identify hidden defects that might not be visible from the outside, ensuring the final part meets strict quality and structural standards. But one of the biggest engineering challenges happens during the actual injection process. Imagine forcing molten aluminum into a sealed mold at enormous pressure. Without enough clamping force, the pressure could literally push the two halves of the mold apart. That is why a Gigapress needs an extremely powerful clamping system to keep the molds securely locked together throughout the casting process. With a proposed 50,000-ton Gigapress, the required clamping force would be enormous. But Elon Musk has made it clear that achieving this level of speed isn't simply a matter of making the machine bigger. Tesla would need an entirely new manufacturing ecosystem around it. That includes extremely fast cooling technology, advanced mold release systems, and intelligent inspection systems capable of checking castings in real time. Together, these technologies could create a manufacturing system unlike anything the automotive industry has attempted at this scale. And this is where Tesla's strategy becomes even more interesting. The 50,000-ton Gigapress isn't just changing how individual car parts are produced. It represents a completely different approach to how an automobile factory operates. Tesla is moving toward a manufacturing model that looks increasingly similar to consumer electronics production. Highly automated, extremely fast, compact, and designed to make maximum use of every square meter of factory space. One of the clearest examples is the dramatic reduction in structural components. Reports suggest Tesla has reduced the number of major structural pieces from roughly 200 in the Model Y to around 80 in the Cybercab. That isn't just a small manufacturing improvement. It represents a fundamental change in how a vehicle can be designed. For more than 100 years, automobiles have been built by connecting hundreds of individual components using welds, bolts, brackets, rivets, and other fasteners. Every additional connection creates another potential point for stress, fatigue, or long-term failure. Tesla's approach is almost the opposite. Instead of assembling a vehicle piece by piece, the company is working toward creating much larger, unified structural castings. The result is a structure with fewer joints and fewer potential weak points. Rather than behaving like hundreds of separate pieces connected together, the chassis can function more like a single continuous structure. That could provide several advantages, including greater rigidity, improved ride quality, sharper handling, and more predictable crash performance. And as Tesla moves toward autonomous vehicles, structural consistency could become even more important. But Tesla may not be finished with factory simplification. After changing how major vehicle structures are produced, the company appears to be targeting another major bottleneck in automobile manufacturing, the paint shop. Painting a vehicle is one of the most expensive, energy-intensive, and time-consuming parts of the manufacturing process. So, Tesla is exploring a much more radical idea. What if the paint shop wasn't necessary in the first place? According to Tesla patents, future vehicle body panels could potentially have their color integrated directly into the material during the molding process. Instead of producing a bare panel and then sending it through several painting and finishing stages, the desired color could become part of the component during manufacturing. Interestingly, newer Cybertruck production vehicles have appeared noticeably glossier compared with the early matte finish prototypes. While this doesn't prove that Tesla has eliminated traditional painting, it suggests the company continues to experiment with alternative approaches. If Tesla could eventually remove or dramatically reduce traditional paint shop operations, the savings could be enormous. Paint shops require huge amounts of factory space, energy, equipment, labor, and maintenance. Eliminating those processes could reduce manufacturing costs while making Tesla's factories smaller, simpler, and faster. And now, another development is attracting attention. Reports indicate that hundreds of Tesla Cybercabs have been spotted at Gigafactory, Texas, with production potentially increasing significantly as Tesla's next-generation manufacturing platform ramps up. At the same time, steering wheel-free Cybercabs have begun appearing in California. These developments suggest Tesla is gradually preparing for a future in which autonomous Cybercabs could play a major role in its robo-taxi network. If Tesla's new manufacturing strategy works as Musk envisions, the Cybercab could become much more than another Tesla model. It could be the first major example of a completely different way of designing, manufacturing, and operating vehicles at scale. With every new update, Tesla's Cybercab is becoming one of the company's most exciting vehicles, while also challenging the belief that Tesla would struggle to produce it at scale. Imagine getting into a car where the doors close automatically, the central screen turns on, and then you realize there is no driver in front of you. There is no steering wheel, no accelerator, no brake pedal, and no traditional controls for a human to take over. A few moments later, the vehicle quietly leaves its parking space, detects pedestrians, understands surrounding traffic, selects the appropriate route, and takes you to your destination without anyone touching the controls. For years, this sounded like another ambitious idea from Elon Musk, but Tesla now appears to be turning that vision into a real transportation system. The biggest evidence is coming from Gigafactory, Texas. Recent drone footage and aerial images have reportedly shown 245 gold-colored Tesla Cybercabs lined up at the factory. These appear to be two-seat autonomous vehicles built for testing and future deployment. Previously, Tesla had prepared more than 100 Cybercabs to transport employees around the factory campus. But the latest developments suggest the project has moved far beyond a few prototypes created for demonstrations. Tesla is now building an entire fleet of vehicles without steering wheels or pedals and testing them in real-world conditions. Eric, who leads Tesla's Cybercab and robotaxi engineering efforts, has reportedly completed around 50 rides in just a few days. While that number may sound small compared with the millions of taxi trips happening worldwide, the important point is that these trips were performed in a vehicle specifically designed to operate without a human driver. Elon Musk has also said that Tesla intends to begin delivering the Cybercab to customers by the end of 2026, with a target starting price of $30,000 or less. Even if that schedule moves into the following year, successfully bringing a purpose-built autonomous vehicle to market at that price would still be a major achievement. At such a price, the Cybercab could potentially attract huge interest from businesses looking to build their own robotaxi fleets and generate long-term revenue from autonomous transportation. There are also signs that Tesla is preparing for wider testing and deployment. Cybercabs have reportedly been spotted being transported on flatbed trucks in San Bernardino, California. Interestingly, the vehicles were seen without steering wheels, suggesting Tesla is actively preparing them for operations outside the Texas factory. But Tesla isn't simply testing another self-driving feature. The company is testing something much bigger: whether a vehicle can completely remove the human driver and still function reliably as a full-scale transportation service. That is why the Cybercab shouldn't be thought of as simply a smaller Model 3 with its steering wheel removed. It is Tesla's first purpose-built robotaxi, developed around a next-generation vehicle platform designed specifically for affordable electric vehicles and autonomous transportation. That difference affects almost every part of the vehicle. A traditional car must be designed around a human driver. It needs a steering wheel, pedals, steering column, instrument cluster, gear selector, and numerous other systems that allow a person to control the vehicle safely. The Cybercab doesn't need many of these components. By eliminating the driver, Tesla can also remove a large number of mechanical parts, wiring, structural components, and potential failure points. This creates a much simpler interior and potentially a lighter, easier to maintain vehicle. It could also make the manufacturing process significantly more efficient, because Tesla doesn't need to install components that exist primarily for human driving. According to specifications referenced in documents associated with the vehicle, the Cybercab has a curb weight of approximately 3,113 pounds. That is roughly 700 to 750 pounds lighter than a standard Tesla Model 3, which is a significant difference for an electric vehicle. A lighter vehicle requires less energy to accelerate and maintain speed. It is particularly useful in city environments, where robotaxis may constantly accelerate, slow down, and stop in traffic. Reducing weight can also help Tesla avoid installing an unnecessarily large battery simply to move the extra mass of the vehicle itself. That creates a valuable chain reaction. A lighter vehicle can require less battery capacity, which can reduce cost and improve efficiency. And when thousands or even millions of vehicles are operating as autonomous taxis, even small improvements in weight, energy consumption, maintenance, and manufacturing cost can become extremely important. This is ultimately what makes the Cybercab so significant. Tesla isn't just trying to build another electric car. It is attempting to create a simpler vehicle, a faster manufacturing process, and an entirely new transportation model, all designed around the idea that the human driver may no longer be necessary. The Cybercab is expected to use a battery pack of around 48 kilowatt hours, which is considerably smaller than the batteries found in many long-range electric vehicles today. Yet, because of its lightweight construction, aerodynamic design, and highly optimized drivetrain, the Cybercab is estimated to deliver around 290 to 300 miles of real-world range. For a robotaxi operating mainly in cities, that could be an ideal combination. Instead of carrying a huge and expensive battery that may rarely be used to its full capacity, the Cybercab is designed to have enough range to stay on the road for hours before returning to recharge. And this highlights an important difference between a personal electric car and a purpose-built robotaxi. Private car owners often prefer the longest possible range because they want the freedom to take occasional long road trips. But most daily journeys are relatively short. A robotaxi has completely different priorities. It doesn't need to satisfy a driver's fear of running out of range. It needs to maximize efficiency. The vehicle needs to know when to charge, when to remain on the road carrying passengers, and how to get the most useful work from every unit of electricity. The Cybercab appears to have been designed specifically around this idea. Tesla claims its drivetrain can achieve efficiency of at least 6.1 miles per kilowatt hour, while some testing has reportedly suggested energy consumption could be as low as around 165 watt-hours per mile under favorable conditions. If those numbers are confirmed in real-world operation, the Cybercab could become one of the most energy-efficient mass-produced electric vehicles ever built. Its efficiency could potentially be far higher than that of vehicles such as the Model 3 and Model Y under certain driving conditions. But the real advantage isn't simply lower electricity consumption. For a robotaxi business, every unit of energy saved can directly improve operating economics. A privately owned car might be driven for only 1 or 2 hours a day. A robotaxi, however, could potentially remain active for 12, 16, or even more than 20 hours per day, provided charging, cleaning, and maintenance are managed efficiently. When even a small efficiency improvement is multiplied across hundreds of thousands of miles, the savings can become enormous. Another interesting feature is the Cybercab's expected drivetrain. The vehicle is reportedly designed around a 219 horsepower electric motor driving the front wheels, which would be different from many current Tesla models that use rear-wheel drive or dual-motor all-wheel drive. Front-wheel drive could simplify the drivetrain, reduce the number of mechanical components, and potentially create more usable space in the rear of the vehicle. The Cybercab is also expected to offer a payload capacity of roughly 617 pounds, which should be enough for 2 passengers and their luggage. Inside the cabin, a massive 21-inch touchscreen is expected to serve as the main interface for the robotaxi. Passengers could use it to monitor their journey, adjust the cabin temperature, control entertainment, unlock the doors, and even instruct the vehicle to pull over or stop. But this leads to a much bigger challenge. Imagine entering a Cybercab for the first time and seeing 2 empty seats, no driver, no steering wheel, and no pedals. The technology may look impressive, but the real question is whether people will trust it. Tesla doesn't simply need to prove that the Cybercab can drive itself. It needs to convince millions of passengers that they can safely place their lives in the hands of an autonomous software system. That could become the biggest challenge of the entire project. The hardware may already be progressing, with more than 100 vehicles reportedly prepared at Gigafactory, Texas. But the factor that will ultimately determine whether cybercabs can operate widely on public roads is the software. In a vehicle without a steering wheel or pedals, full self-driving cannot simply work correctly most of the time. It needs to handle virtually every part of a journey safely, without requiring a human to take control. That is why Tesla has been testing cybercabs with employees inside the controlled environment of Gigafactory, Texas. Testing within the factory grounds allows Tesla to expose the vehicles to real-world situations while maintaining greater oversight than would be possible on public roads. At the same time, Tesla is working toward making its full self-driving system more personalized. For example, if a driver repeatedly corrects the system in a specific situation, such as staying in a faster lane instead of moving into slower traffic, future versions could potentially learn from that intervention. And remember the driver's preference. For a conventional Tesla, personalization can improve the driving experience. But for the Cybercab, the stakes are much higher. Because there is no human driver waiting to take over, the software must eventually become reliable enough to make the right decisions on its own. That is what will determine whether the Cybercab becomes just another experimental Tesla project, or the beginning of a completely new era of autonomous transportation. Tesla appears to be developing an automated cleaning system to handle this task. Company documentation describes a cleaning robot equipped with a large robotic arm and an automatic tool-changing system. The robot could switch between different attachments depending on the job. One tool could vacuum the cabin, another could pick up objects such as plastic bottles and aluminum cans, while a microfiber attachment could clean delicate surfaces. It could even retrieve belongings that passengers accidentally leave behind, such as backpacks or other personal items. The microfiber tool is designed to clean areas including the Cybercab's 21-inch touchscreen, windows, windshield, buttons, and door handles without damaging their surfaces. Forgotten items could potentially be placed into a dedicated lost and found compartment, allowing the vehicle to return to service without waiting for a human employee to deal with every small issue. Tesla has also suggested that passengers could potentially be charged an automatic cleaning fee if they leave excessive trash inside a robotaxi. The idea is simple. Automate as much of the cleaning process as possible, reduce operating costs, and encourage passengers to keep the cabin clean. Tesla is also exploring automated exterior washing. After completing multiple trips, a Cybercab could potentially drive itself to a service facility, pass through an automated wash, receive interior cleaning, and then return to passenger service without requiring a human driver. The company has even developed technology involving UV-based sanitization, designed to disinfect the cabin between rides by reducing bacteria and other microorganisms. All of these systems are designed around one goal: keeping the vehicle on the road for as much time as possible while minimizing human intervention. Energy efficiency is another major part of the strategy. Tesla expects the Cybercab to achieve at least 6.1 miles per kilowatt hour, potentially making it dramatically more efficient than vehicles such as the Model 3 and Model Y in certain driving conditions. Tesla's 2025 impact report has also stated that its full self-driving system can operate around 5% more efficiently than the average human driver. Combine that software efficiency with a lightweight body, a relatively small 48 kilowatt-hour battery, and Tesla's next-generation vehicle platform, and the Cybercab could spend more time carrying passengers while consuming less energy. Tesla has also reported that the greenhouse gas emissions associated with operating its electric vehicles can be a fraction of those produced by conventional gasoline-powered vehicles. Of course, electric vehicles aren't completely free of emissions. Some indirect emissions still come from the electricity used to charge them. However, as electricity grids increasingly rely on renewable sources such as solar and wind, the emissions associated with charging electric vehicles can continue to decline. Tesla is also attempting to reduce emissions during the manufacturing process itself. One example is the company's reaction injection molding approach for certain Cybercab body panels. Instead of producing a panel and then sending it through a traditional automotive paint shop, the color can be integrated directly into the molding process. This can dramatically reduce processing time, from several hours to only a few minutes. Tesla says the process can also reduce greenhouse gas emissions across the supply chain and manufacturing process for the affected components while eliminating volatile organic compound emissions associated with conventional automotive painting. And this is what makes Tesla's next-generation vehicle platform so important. The company isn't simply taking a traditional car and removing the steering wheel and pedals. Tesla is attempting to redesign the entire vehicle around autonomous transportation. That means removing unnecessary components, simplifying manufacturing, reducing energy consumption, automating cleaning and maintenance, and lowering the operating costs of every vehicle. The ultimate goal is a robotaxi that can drive itself, clean itself, recharge itself, and return to service with as little human involvement as possible. If Tesla can make all of these systems work reliably at scale, the Cybercab could represent something much bigger than a new Tesla model. It could become the foundation of an entirely new transportation system, one designed from the ground up for autonomous vehicles.